Hello everyone. It's fantastic to be here on the 150th anniversary of Hupley. Happy birthday, Hupley. I'm going to talk about the subject matter of one of my books, Gravitational Waves. At Hanford in Washington State in America is a 4-kilometer ruler made of laser light. 3,000 kilometers away in Livingston, Louisiana is another 4-kilometer ruler made of laser light. On the 14th of September 2015, a shudder went through the Hanford ruler. And 100th of a second later, a shudder went through the Livingston ruler. And here are the signals. The top panel, the orange panel, shows you the stretching and squeezing of the Hanford ruler. So the up and down motion you're seeing is the stretching and squeezing. And all of this happens over a space of about 1/10 of a second. And the middle panel, the blue panel, the up and down motion of the trace shows the stretching and squeezing of the Livingston ruler. And on the bottom panel, you can see the two signals overlaid, and they are virtually identical. And this is the unmistakable signature of a gravitational wave, a ripple in the very fabric of space-time predicted by this man about 100 years earlier. This is Albert Einstein in his bodybuilding phase. I really like his E=mc² tattoo on his shoulder. Now, the discovery of gravitational waves was very, very significant. Imagine you've been deaf since birth, and then suddenly, overnight, you can hear. That's what it's like for physicists. Throughout history, they've been able to see the universe with their eyes, and more recently, they've been able to see it with their telescopes. But now, for the first time, they can actually hear the universe. Gravitational waves are the voice of space. Now, it's very often that scientific discoveries are overhyped, but it's fair to say that the discovery of gravitational waves on the 14th of September 2015 was the most important development in astronomy since Galileo turned his telescope on the heavens in about 1609. Now, what gravitational waves tell us is that space is a thing. It can be bent and twisted and rippled, just like the surface of a pond. And this idea is a prediction of Einstein's theory of gravity, which he presented in 4 lectures in November 1915 at the height of the First World War in Berlin. Now, Isaac Newton had imagined that the force of gravity was like an invisible tether connecting the Earth to the sun. And that tether kept the Earth trapped in orbit around the sun. But what Einstein showed is that was incorrect. What a big mass like the sun actually does is it curves or warps the space-time around it into a valley. Now, it's a valley in 4-dimensional space-time, which we cannot see. That's why it took the genius of Albert Einstein to notice it. And the Earth travels around the upper slopes of this valley around the sun, just like a roulette ball in a roulette wheel. So how do you actually create gravitational waves? Well, what you have to do is accelerate mass. You have to move mass violently. Okay, can we all put up our right hand now? Okay, can we wave our right hand? Okay, now put it down. All of us have generated gravitational waves. They've spread outwards from our hands. They've passed already beyond the top of the atmosphere. They've passed beyond the moon, and they're well on their way now to the planet Mars. Now, the nearest star system is called Alpha Centauri, and it's 4 about 4.5 light years away. It's a triple system of 3 stars. And recently we discovered that one of those stars has a planet around it. Now, if that planet has a technological civilization and they've built a gravitational wave detector, they will pick up the gravitational waves that you created with your hand in about 4.5 years' time. So in the spring of 2025. There is a proviso, and that is that the gravitational waves you created with your hand were very weak. And the reason for this is that it's very hard to make gravitational waves. This is Richard Feynman, probably the most famous post-war American physicist. I was fortunate enough to be taught by him when I was a student at Caltech, the California Institute of Technology in Pasadena. Now, he was famous for co-devising the theory of how light interacts with matter, and he got the Nobel Prize for that. But he was also famous for playing the bongos. Now, when you play the bongos, it's easy to make a sound because it's easy to flex and vibrate the drum skin. But it turns out that space-time is like a drum skin, but a drum skin which is 1 billion times stiffer than steel. So you can imagine if you had some bongos and the drum skin was 1 billion times stiffer than steel, how difficult it would be for you to make them vibrate and create a sound. I'm going to emphasize again how difficult this is to do. This is a nuclear submarine. Now, nuclear submarines are huge. They can be up to about 150 or 200 meters long, so about twice the diameter of the Colosseum in Rome. And a nuclear submarine can weigh something like 50,000 tons. That's about 10,000 times the weight of an elephant. Now, this is a merry-go-round. Imagine that we could put that nuclear submarine on this merry-go-round and spin the merry-go-round faster and faster and faster until almost the point when the metal of the nuclear submarine was about to fly apart. That would generate gravitational waves. Now, this is an ant climbing a vertical wall. Imagine if it fell a centimeter onto your hand. Imagine what that would feel like, the amount of energy that would be dissipated. Well, the energy dissipated by the ant falling a centimeter is 1 billion times greater than the energy in the gravitational waves produced by that spinning nuclear submarine. I mean, it's a really weird comparison I've given you, but hopefully it emphasizes just how difficult it is to create gravitational waves. So in order to actually create appreciable gravitational waves that we have any chance of picking up on the Earth, we require the violent motion of some of the most massive objects in the universe. So what created the gravitational waves that we picked up on Earth on the 14th of September 2015? Well, in a galaxy far, far away, at a time when the most complex organism on Earth was a bacterium, 2 monster black holes were locked in a death spiral. They whirled around each other one last time, they kissed and coalesced, and in that moment, they launched a tsunami of gravitational waves, which spread out at the speed of light. And I want to give you some idea of the energy in those gravitational waves. This is a nuclear fireball, the fireball of a hydrogen bomb. Fortunately, we don't explode hydrogen bombs in the atmosphere anymore. But typically when one of these bombs was exploded, something like 1 kilogram of mass was destroyed. In other words, 1 kilogram of mass energy was converted into other forms of energy eventually the heat of the fireball. So remember that, 1 kilogram. Well, in the merge of those two black holes that we picked up, in an instant, 3 times the mass of the sun was destroyed. And it reappeared immediately as gravitational waves. So 3 times the mass of the sun. Can you believe that? The amount of mass energy that was actually in those gravitational waves. So it turns out that the power in those gravitational waves was 50 times greater than the power emitted by all the stars in the universe together. So to put it another way, had that merger of two black holes not created gravitational waves, but created visible light that our eyes could see instead, that single event would have shone 50 times brighter than the whole universe. That is the single most violent event that had ever been observed up until that moment. Now, those gravitational waves, like ripples on a pond, spread outwards. And they spread out for 1.3 billion years. And just like the ripples on a pond, they got weaker and weaker as they filled a greater and greater volume of space. They became more and more diluted. Then eventually, on the 14th of September 2015, they passed through the Earth. And as they did so, they stretched and squeezed everything in their path. Did you feel a bit queasy on the 14th of September 2015? Well, if you did, it was probably something you ate the night before, because the effect was incredibly small. So to give you some idea, I've already mentioned Alpha Centauri. Alpha Centauri, the nearest star system to the sun, is about 4.5 light years away. It would take our fastest ever space probe, one of the Voyager probes, something like about 80,000 years to get to the nearest star, Alpha Centauri. But when these gravitational waves passed between the sun and Alpha Centauri, they stretched and squeezed the space between them by 1/100th of a millimeter. And to put it another way, the 4-kilometer rulers at Hanford and Livingston were stretched and squeezed by 100 millionth the diameter of a single atom. Here is the ruler at Hanford. It's basically a 1.2 meter diameter tube, which is evacuated so that it has a much better vacuum in an empty space, and down which about a megawatt of laser light is pumped. And I actually lied to you, because at each of these sites, Hanford and Livingston, which are collectively known as LIGO, the Laser Interferometric Gravitational Wave Observatory, there are actually 2 4-kilometer rulers. So this is how these detectors work. So you can imagine laser light pumped in on the bottom left-hand corner arrives at what we call a beam splitter. Now, a beam splitter is just a stupidly technical name for something really mundane, which is a half-silvered mirror. So what happens is the laser light, half of it goes straight through the mirror to the top right, and the other half is reflected to the top left. And when the laser light along the 2 paths gets to the end of the 4-kilometer rulers, there are mirrors which reflect it back. So the light comes back to the beam splitter, is recombined, and comes out at the light detector on the bottom right. Now it turns out that if, when the light is recombined at the beam splitter, the crests of one wave train coincide with the crests of the other wave train, then the light is boosted. So we would see a very bright light at the light detector. However, if the crests of one wave train coincide with the troughs of the other, they cancel out, so we'd see no light. So immediately you can see that this instrument, which we call an interferometer, is very sensitive to changes in the length of one of these arms, one of these 4-kilometer arms relative to the other, of about the wavelength of light. And the wavelength of visible light is about 1/1000th of a millimeter. So it's very, very tiny. So already you can see this instrument is very sensitive to small changes in arm length. But of course, it's a long, long way from 1,000th of a millimeter to 100 millionth the diameter of an atom. And a lot of technology was involved in getting to that level. Well, this is actually one of the mirrors at the end of one of the 4-kilometer tunnels. They weigh 43 kilograms. They're suspended by fibers, which are only twice the width of a human hair. And they reflect something like about 99.999% of the light that comes on them. And it's the movement of these mirrors back and forth that signals the passage of a gravitational wave through the instrument. Now, in effect, what LIGO is the world's best seismometer. It's so sensitive that it can detect storms on the other side of the country. It's so sensitive that it can detect the vibration caused by cars going over bumps on roads tens of kilometers away. It's so sensitive, it can pick up the vibration caused by cyclists going past one of the sites. It's so sensitive, it can pick up the crashing of waves on beaches hundreds of kilometers away. In fact, it can pick up pretty much every single earthquake on the Earth. So you can see the problem in detecting gravitational waves. You've got to detect a fantastically small change in the length of one of those 4-kilometer rulers, and you've actually got to screen out all these spurious vibrations at the same time. So it's no wonder that the discovery of gravitational waves on the 14th of September 2015 earned the Nobel Prize for some of the physicists involved. Here are the 3 pioneers of LIGO. On the left is Ray Weiss, who is an experimentalist at MIT, the Massachusetts Institute of Technology near Boston. And on the right is Kip Thorne, who's a black hole theorist at Caltech in California. But I want to focus on the man in the middle. His name is Ron Drever. And when I was at Caltech, I went to a lecture given by Ron Drever. And I remember he came in, he was a short, dumpy man, and he carried his notes into supermarket carrier bags. And his overhead projector slides were all covered in fingerprints and tea stains. And I wondered why he was at Caltech, which is often ranked the #1 university in the world. Well, it turned out he was an experimental genius. In 1953, he had built a television from scratch so that his family could watch the coronation of Queen Elizabeth II, the Queen of England. And he then pioneered gravitational wave detectors at the University of Glasgow, and he was poached by Caltech. But the story of Ron Drever is quite sad because he was apparently incapable of sharing control of the project. And in 1991, he was fired by the man on the right, Robbie Vogt, and was no longer able to work on LIGO. He kept his professorship at Caltech and his office, and he would go into work every day, but he was kept away from his brainchild. Eventually, he got Alzheimer's disease, dementia, and one of the professors at Caltech, Peter Goldreich, flew him to New York, put him on an aeroplane back to Glasgow in Scotland. He was met by his brother, and he went into a care home. And when the gravitational waves were discovered, I'm a big user of social media, in particular Twitter. I kept tweeting to the Nobel Committee, hurry up, give the prize quickly. But unfortunately, they were too late, and Ronald Drever died a few months before the award of the Nobel Prize. So he didn't actually get it, and Scotland was cheated of a Nobel Prize. So that's a sad story. A more happy story is that this man, an Italian, Marco Drago, was the very first person in human history to see the signature of a gravitational wave. He was working in Germany, in Hanover, and he was the person who opened the email that contained those two traces that I showed you at the beginning of my lecture. Now, everyone thought the discovery of gravitational waves was worthy of a Nobel Prize, but some people thought it was worthy of the X-Files. One of the scientists working on LIGO was on an aeroplane coming into Baton Rouge near Livingston, and the passenger sitting next to him leant over, pointed down at the instrument on the ground, which you can see here, and he said, "They're building a time machine down there. One of those arms goes to the future and the other goes to the past." Well, it was a fabulous instrument, LIGO, but not quite that fabulous. So what has LIGO discovered? Well, LIGO has discovered around 10 black hole mergers now. And those have been very surprising because they've involved black holes much bigger than we predicted we would find. Now, black holes are the end point of the evolution of massive stars. When a massive star gets to the end of its life, it explodes as a supernova. But paradoxically, the core of the star actually implodes. In fact, it's the implosion of the core that drives the explosion of the supernova. And as the core shrinks smaller and smaller, its gravity becomes more and more intense until eventually it becomes so intense that light cannot escape and a black hole is formed. The problem is that something like 90% of the mass of the star is actually blown into space, and only 10% ends up as the black hole. And we have seen black holes of about 50 times the mass of the sun. That implies that the stars from which they were born were about 500 times the mass of the sun. Now, such stars are pretty much non-existent in today's universe. But it could be that we are seeing an earlier generation of stars. Now, after the Big Bang, there was a first generation of stars to form. And when they exploded, a second generation formed out of their debris. And when that generation exploded, a third generation formed from their debris. And our sun is a third generation star. But there are theoretical reasons to believe that the very first generation of stars were monsters. So in these mergers of black holes that LIGO has seen, it could be we're seeing black holes which formed from the very first generation of stars. So that's really like walking around Milan today and finding a legionnaire, a Roman legionnaire who's lived in the city and survived since the fall of the Roman Empire. But there is another exciting discovery that LIGO made on the 14th of August 2017. By that time, it was joined by a third gravitational wave ruler, which is at Pisa or near Pisa in Italy. Now, there's an interesting story behind this discovery, so bear with me. In the 1960s, the Americans and the Russians signed a test ban treaty. They decided not to explode hydrogen bombs in the atmosphere. But the Americans were very worried that the Russians would violate the treaty. So they put into orbit spy satellites. And those spy satellites were able to detect gamma rays, high energy light given out by nuclear fireballs. Well, to the surprise of the Americans, their satellites showed a burst of gamma rays on average about once every day. Fortunately, those spy satellites had a directional capability, and they were able to determine that the gamma ray bursts came not from the ground, but from outer space, thus avoiding an accidental nuclear war. Now, the existence of these gamma ray bursts once every day somewhere in the universe was kept a secret by the Americans until the 1980s, when they finally revealed this discovery to astronomers. And astronomers began to think, what could create these gamma ray bursts once a day? And they came up with this idea that they thought it was the merger or collision of neutron stars. Now, neutron stars are the endpoint of the evolution of massive stars like black holes, but they are stars which are less massive. And neutron stars are something like the mass of the sun concentrated into a volume about the size of Mount Everest. So the idea was when the two of these neutron stars spiraled together and merged, they would create a burst of gamma rays. Well, on the 14th of August 2017, when LIGO Virgo picked up gravitational waves from a merger, satellites in orbit also picked up a burst of gamma rays. So it was proved that neutron star mergers were the source of the mysterious gamma ray bursts. But there was something else interesting. And for this, we need to go back to the 1950s. This is Fred Hoyle, a British cosmologist, famous for coining the term Big Bang in a BBC radio broadcast in 1949. He and his colleagues in the 1950s figured out where all the elements in your body come from. The iron in your blood, the calcium in your bones, the oxygen that fills your lungs every time you take a breath. According to Hoyle and his colleagues, all of these were built up by nuclear reactions inside stars that lived and died and blew up before the sun and the earth was born. So you are stardust made flesh. You were literally made in heaven. Well, it turns out that there was a gap in the knowledge of Fred Hoyle and his colleagues. They could figure out where pretty much all the elements came from, but they didn't know where silver and gold came from. But it turns out that the gamma rays that accompanied the gravitational waves, which were picked up on the 17th of August 2017, showed the signature of gold. In fact, they showed that the merge of those two neutron stars had created 20 times the mass of the Earth in gold. So if you've got a gold watch or a gold necklace, that's where the gold came from. So we tend to think of the universe out there as a long way away and remote from our everyday lives. But actually, if you've got a gold watch or a necklace, that gold was created in a merger, a catastrophic merger of two neutron stars long before the Earth and the Sun were born. Can there be a more striking example of how connected the nearby and everyday is to the faraway and cosmic? So what now for LIGO and Virgo? Well, this is where the two detectors are in America, and I lied to you, they're not 3,000 kilometers apart, they're 3,002 kilometers apart. So the plan now is to add more of these detectors. This is Virgo, the European gravitational wave detector near Pisa. So we now have 3 gravitational wave detectors working in concert. The idea is to add another one in Japan and another one in India. GEO, or GEO 600, is a British-German gravitational wave detector, which is not big enough to actually detect gravitational waves, but it's where a lot of the technology is actually developed. There is even a plan to put a gravitational wave detector in space. This is LISA, the Laser Interferometric Space Antenna. And the idea is to launch 3 satellites, which will orbit as the corners of an equilateral triangle. The sides of those of the triangle will be something like 1.2 million kilometers. And as a gravitational wave passes, it should change, stretch and squeeze the sides of the equilateral triangle, and that should be measurable. And this will enable us to detect, we hope, the merger of supermassive black holes in the hearts of galaxies. Now, we've detected gravitational waves from black hole mergers and neutron star mergers. Both of those were predicted ahead of time. But what's most exciting about developing this new sense, this sense of hearing that we didn't have before, is that we hope to find many unexpected things. And maybe we can get some indication of what we might hope to detect by looking at the electromagnetic spectrum. Now, in the 1860s, the Scots physicist James Clerk Maxwell realized that light was an electromagnetic wave, a wave in the invisible electric and magnetic fields that permeate all of space, a ripple in those fields. And he realized that the difference between red light and violet light was that the vibrations of this electromagnetic field were more sluggish in the case of red light than they were in the case of violet light. And he realized also his theory put no constraint whatsoever on how fast or how slow these electromagnetic waves, these light waves, could vibrate. So he realized immediately there must be millions of invisible colors. So beyond the red end of the rainbow or the red end of the spectrum, there are invisible colors, vibrations of the electromagnetic waves, which are more sluggish than red. We call them infrared and radio waves. And on the other side of the spectrum, beyond violet light, are vibrations of electromagnetic waves which are more rapid than violet, and we call them ultraviolet, X-rays and gamma rays. And after the Second World War, we developed the technology to see these invisible colors, and they have given us many, many surprises. So, for instance, we have discovered extrasolar planets, planets around other stars. And currently there are about 5,000 planets that we've actually discovered. And we've discovered supermassive black holes. It turns out that the center of every galaxy in our universe, all of the 2 trillion galaxies, appears to have a supermassive black hole in it. Now, some of these supermassive black holes are up to 50 billion times the mass of the sun, but we've just got a tiny one in the heart of our Milky Way galaxy. It's only 4.3 million times the mass of the sun. And we discovered gamma ray bursters. These are, as I was saying, the merger of neutron stars. They produce oppositely directed bursts of gamma rays. And if one of these mergers happened even within a few thousand light years of the Earth, and one of these beams was pointing at us, it would endanger life on Earth, because the gamma rays would actually destroy the ozone layer, which protects the Earth from dangerous radiation from the sun. And when we looked throughout the electromagnetic spectrum, we also discovered the afterglow of the Big Bang. We call it the cosmic background radiation. It exists because the heat of the fireball of the Big Bang had absolutely nowhere to go. It was bottled up in the universe, which by definition is all there is. And so we see it all around us today, greatly cooled by the expansion of the universe in the last 13.82 billion years. So it no longer appears as light that we can see with our eyes, but it appears as microwaves, a form of radio waves. And it turns out, incredibly, that 99.9% of all the photons, that is particles of light in the universe, are tied up in this afterglow of the Big Bang, and only 0.1% are tied up in the light from stars and galaxies. So maybe all these unexpected discoveries that we made when we opened up the electromagnetic spectrum will give us some hint as to what we will discover as we open up the gravitational wave spectrum. And here is the gravitational wave spectrum. It's analogous to the electromagnetic spectrum because gravitational waves can vibrate at any rate. So to the right-hand side of this white bar in the center, we see very rapid vibrations of gravitational waves. And these are produced by the things that we've already seen, the merger of neutron stars and black holes. And to the right are the very sluggish vibrations of gravitational waves, ones which last maybe a month or a year, something like that, and they would be produced by supermassive black holes. So by analogy with the electromagnetic spectrum, we would hope to find completely unexpected things. So where are we? So we have built the crudest possible gravitational wave detectors. And at the very limit of audibility, we've detected the equivalent of the sound of thunder. But we're yet to detect the gravitational equivalent of a bird singing or a baby crying or of music. And as we continue to improve our gravitational wave detectors, who knows what we'll detect as we tune in to the cosmic symphony. Thank you.